Hello and welcome to an explanation of the Hardy-Weinberg equation. You may be doing this for extra credit and an opportunity to really learn a little bit more in depth how genetics works. And I'm just going to read this statement here. I think it's kind of an important one to go through. It says, sometimes it's fairly easy to determine if you have a genetic disorder. The symptoms can be very obvious. However, just because you don't have a particular genetic disorder doesn't mean you don't carry it. People go to genetic counselors who collect information about your family history and build a pedigree, as you may have already learned or will learn about soon in genetics. From these pedigrees or family stories and trees, using a mathematical equation, they can determine the chance that you are a carrier. Not the chance that you have the disorder, that's a separate equation that we'll take a look at, but just a chance that you carry that. In other words, that you're heterozygous or a hybrid individual. You yourself are going to be fine throughout your entire life, but there's a possibility that you could pass this trait on to your kids, or at least the recessive gene. And if the person that you decide to have kids with is also a carrier, well, then there's that possibility that your kids will have this genetic disorder. And so this equation is designed to help us figure out how common the carriers are. You did your research for your assigned genetic disorder and found that only 1 in 100,000 people perhaps have this assigned genetic disorder. And so finding an individual who has that would be relatively rare. When we take a look at Madison, for example, with 300,000 people, there would only be 3 individuals who have that assigned genetic disorder living there. And yet, the number of people who carry that recessive gene are going to be significantly higher. This equation will help us figure out how common the carriers are. And that's essentially a definition of the Hardy-Weinberg equation. It's an equation used to figure out how common the carriers are based on knowing how often a trait is inherited. We're going to need to define some terms here. Frequency, how often something occurs, usually written as a decimal. So for example, when we say 1 out of 4 people have blue eyes, if that's the case as the result of a Punnett square, we know that we can convert that to 25%. But for the Hardy-Weinberg equation, we'd want to note that as a decimal. So as a decimal, 25% of course is 0.25. Take your percentage, 25%, divide that by 100, and you would end up with your decimal. So we're going to be working with frequencies here, always recorded as a decimal. We're also going to cheat a little bit. We're not going to use the traditional code for using dominant recessive, like a capital letter and a lowercase letter, other than I'm going to use a capital D for dominant and a lowercase r for recessive. Won't matter what trait we're talking about, but we can always use a capital letter there and a lowercase letter, and I'll show you why I'm doing this in just a second. Something else to know is that all the genes present in a population would be a combination of the frequency of the dominant genes plus the frequency of the recessive genes. In other words, if we take a look at a population, that for each individual having pairs of genes, how many dominant genes do you see and how many recessive genes do you see? And of course, added together, we should end up with all of them. Or capital D, dominant, plus lowercase r, recessive. The frequency of each of those added together is going to be 1, or 100%. Example, 75% of people have the brown eye gene, if that was the case, while 25% of the people have the blue eye gene. That adds up to 100%. If we only knew the percentage of individuals that had the brown eye gene, we could figure out the percentage of people that have the blue eye gene, because it has to add up to 100%. 0.75 plus 0.25 is equal to 1. In this equation then, to take a look at the Hardy-Weinberg equation, we're going to set up a situation where we cross 2 hybrid individuals. Now hybrids, in this case, using this notation, we would have 2 individuals that are big D, little r, a dominant gene and a recessive gene. And when you solve that Punnett square, what we should end up with are big D individuals, big D little r individuals. In fact, we should have two of them, and little r individuals. And then certainly we have individuals that are homozygous dominant, heterozygous dominant, and homozygous recessive. The frequency of the purebred dominant individuals would be D squared. D squared meaning the frequency of the dominant genes squared should give us an idea of how many, or the chance that someone is a purebred dominant individual. The frequency of the hybrid individuals, the hybrids being dominant and recessive, would be the dominant frequency times the recessive frequency, and then two of them, because there are two in this Punnett square. And in addition, we also have the purebred recessive individuals. They would be the frequency of the recessive genes times the frequency of the recessive genes. In other words, r squared. And if we take all those individuals, the homozygous dominant, the heterozygous, and the homozygous recessives, all added together should be 100% of the individuals. So the Hardy-Weinberg equation would say that d squared plus 2dr plus r squared is equal to 1. Again, the r squareds are the only ones that have the recessive trait, and the 2drs, the 2 times the dominant frequency times the recessive frequency, would be our carriers. Some other things to note about the Hardy-Weinberg equation. Again, D plus R, the frequency of the dominant genes plus the frequency of the recessive genes, is equal to 1. Those that have the recessive trait, R times R, the frequency of the recessives squared. And the carriers would be 2 times the frequency of the dominant times the frequency of the recessive genes. Show you how this all works. Show you how this puts together for us how common the carriers are. So we're going to use a sample problem here where indeed tongue rolling is a genetic trait. If you are able to roll your tongue, you have at least one dominant gene because that particular gene is dominant. And if you're unable to roll your tongue, well, non-tongue rolling is a recessive gene. And so if you can't roll your tongue like this individual here is able to, if you can't do that, then you would be little t, little t. And as it turns out, 36% of the population are non-rollers. So how common are the carriers of the dreaded non-tongue rolling gene? Step 1 in these problems would be to figure out the frequency of the recessive individuals. We know that 36% of the population are non-rollers. To be a non-roller, you would have to be little t, little t. So the frequency of little t would be 36%, but remember, we need to put this into decimal form. So the frequency of little t recessive individuals, the non-rollers, would be 0.36. Okay. If that's t squared, then we need to solve for the frequency of the t genes. T squared is equal to 0.36. So if we solve for t, we would take the square root of t squared to get to t. And so we're going to take the square root of 0.36. And I want you to have your calculator handy so you can see how this works. I want you to put 0.36 into your calculator and take the square root of that. And what you should end up with as a frequency for the t genes would be 0.6. Double check. Make sure that you're getting that. If you're not sure how to put that into your calculator, let me know. All right. Well, that's how common the recessive genes are, the non-tongue rolling genes are. We also need to know how common the dominant genes are, the tongue rolling genes. And if we go back to what we know from the Hardy-Weinberg equation, we know the dominant genes plus the recessive genes would be equal to 1. In this case, we already know how common the recessive genes are. So the dominant genes plus 0.6 would be equal to 1. Or in other words, big T, the dominant tongue rolling gene, would be equal to 0.4. To back up for a moment, What this would mean is that 60% of the genes that are out there are recessive, and 40% of the genes that are out there are the dominant genes. To figure out the carriers, remember for the Hardy-Weinberg equation that the carriers would be 2 times the dominant genes times the recessive genes, or in this problem 2 times capital T times lowercase t. Since we've already solved for those frequencies, we can plug that right into our equation. 2 times 0.4, the dominant frequency, times 0.6, the recessive frequency, would give us 0.48. If we convert that back to a percentage, multiply 0.48 times 100, then what the Hardy-Weinberg equation would say is that 48% of the population are carriers of that non-tongue rolling gene. So they themselves, of course, would be able to roll their tongue just fine, and of course there are others that are big T individuals. But there's that possibility that with that 48% of the people that carry that dreaded gene, that they'd pass on to their kids the inability to roll their tongue. Now, you know, big deal, so you can't roll your tongue, right? But the same sort of approach can be used to figure out how common the carriers are for any genetic disorder, at least ones that are dominant and recessive. And so you have a variety of additional problems to work through to take a look at cystic fibrosis and sickle cell anemia and a whole bunch of other ones. PTC tasters, tasting a bitter chemical on a piece of paper. If you want to try this out, I've got plenty of this paper. You could try this out. And in each case, we want you to solve for how common the carriers are. And then ultimately, you're going to be given the chance to do the same thing with your assigned genetic disorder. And so we have some answer keys available. I'm going to have you come to me in order to take a look at if your answers are correct or not. But then you're going to apply this to that broader genetic disorder. And I'd like to see that as part of your genetic disorder brochure. When you're trying to address that question, where did this come from? How did I get this? You should be able to describe how common the carriers are for this assigned genetic disorder if you want to earn full credit for the extra credit. If you have questions, let me know. Otherwise, good luck in solving these problems. I think you'll learn quite a bit.